Assalamu alaikum and greetings. This is Dr. Bilal Wajid. So, in the last lectures, we introduced the Fourier transform, and we had a separate lecture on the impulse function. And the impulse function is an important function, and it is useful, and it is used highly. Therefore, there was a need to have a separate lecture for that, although it may be brief. Now we're going to go back to the Fourier transform, and we will talk about some of the properties. These are some of the properties of the Fourier transform. So if you have f of t, which is the signal, the Fourier transform is f omega. And these are some of the basic properties. Now, this particular chapter does not, rather deals with these properties from a qualitative perspective. We won't be discussing all the properties. We would rather be focusing on the ones which you would see a lot in the coming chapters. So one of the property, for instance, is the shift property. So it means that if a signal, and so in the first case, for instance, if f of t's Fourier is f omega, then the shifted version of the signal will look something like this. If you look at this, what we added here is an exponential component. Adding an exponential component means the magnitude does not change. The only thing that does change, however, is the phase component, but the magnitude doesn't change. Now, there are two analogies for that I've highlighted here. One is the gramophone. So if you hear some music today, and let's say you hear the music tomorrow, the same music tomorrow, it doesn't sound any different. The magnitude remains the same. At the same time, your mood may not change based on the music. The music will hear the same, but the mood may not be the same. Another example is if you use a microscope and you're looking at a specimen underneath the scope, even if you shift it by left or right, the original image remains the same. Therefore, what we're trying to focus here is that a shift in time domain does not change the magnitude of the Fourier transform. It does, however, change the phase. So for instance, in this case, in this animation, your orange is the original image and the blue is the shifted version in time. Now this is the Fourier transform of the same. Now, what is worthwhile noticing here is that the higher frequency components, these are the lower frequency components, their magnitude does remain the same, but their phase changes, and that's why they are rotating. However, the other important thing is that the higher frequency components tend to move faster in phase as compared to the lower frequency components. The other useful property is differentiation. Now, going back to this, in differentiation, okay, it's not mentioned actually over here. If you differentiate, so if y of t corresponds to y of f, now the derivative of this, the Fourier transform of this, adds this component. The double derivative squares this. The nth derivative raises it to the power n. Now what this means is that differentiating in time domain may be harder to solve, but one can always find the Fourier transform of that and just add the component 2 pi if along with it, raised to the power how many times you differentiate. Now this makes the mathematical operations easier because your derivatives are converted into simple linear algebra or algebraic formulations, which are always easier to solve. Another important property is that of scaling. So if g of t corresponds to g of f, and if you scale the function, scaling the function, for instance, let's assume that you compress the signal. Now compressing a signal for a periodic signal, let's say, now if your signal was, let's say, the time period was 10 seconds, and you compress the signal by a degree of 2, so now the time period is 5 seconds. That means initially, if it took 10 seconds for one signal or to complete, now by compressing the signal by degree of 2, you have 2 signals that cover the same time span, because the time period is now 5 seconds. Now what you notice here is that by compressing the signal by a degree of 2, you have doubled the frequency. It means in the same time frame, now the signal is repeating twice. Therefore, what is important to understand here, that a compression in time domain is equivalent to an expansion in the frequency domain, because frequency is the inverse of time period. Therefore, you have this formulation. Now another important, and this is very useful, and you would see this in the later coming chapters when we discuss with two-dimensional signals like images. And why is it particularly important to look at signals in frequency domain, or look at images in frequency domain? And one of the very fundamental properties of Fourier of frequency domain is that a convolution in time domain is equivalent to multiplication, and multiplication in time domain is equivalent to convolution. Now if you pass a signal f through a system with an impulse response h, the output will look like g. Now convolution is always a hard task. You can in fact circumvent this by just finding the Fourier transform of the individual f and h and then multiplying it to get g. And then you can find the inverse Fourier transform of g to get your signal in time domain. This step is usually easier than this step. Now an extremely important property for linear systems is the principle of superposition. Now superposition says that if you have a cart and you're pushing the cart with a force P, then the distance the cart covers is A. By the same token, if you push the cart with a force Q, the distance that it will travel is B. Now if you push the same system with a force P plus Q, then the output, the distance the cart will move, will be the sum of A plus 2. Now that's a fundamental property of linear systems, and this is a property which is called superposition, that the sum of the inputs will lead to a sum in the outputs. Now this is for instance, if you have a system and given an impulse, you have an output which is g of t, which technically is called the impulse response to the system. Now if the system is time invariant, what will happen is that if this original signal is delayed by a time t0, then the output will look exactly the same as the original signal, only that it would be delayed. So delaying a signal does not change how the output looks like. That is called time invariance. A system is linear if the input is scaled, the amplitude is scaled by an amount k, then the output g of t will also be scaled by the same amount. If something like this happens, the system is called a linear system. Now a combination of these two is called a linear time invariant system. So here is the original signal, you scale it by k, the magnitude. Here is the output is scaled, and again if you delay the signal by tau, the output is also delayed by amount tau. So this is called an LTI system. Now linear time invariant systems are extremely important is because most of the non-linear systems under certain conditions can be approximated to act like linear models. So rather than dealing with, and especially at an introductory level, rather than dealing with complex, difficult, non-linear questions, you try to deal with mathematics, which is easier. One good example here where replacing the convolution with the multiplication really helps. So if you have a signal p of t, which is your input, the output q of t, then h of t is the impulse response of the system. Now the impulse response of the system, the same thing in convolution, when you look at it in Fourier domain, the same thing looks like a multiplication. Now this h of s is called the impulse response. Now if we replace the input p of f with an impulse which is delta t, the Fourier of that is 1. And what you see here is that the h of f becomes the q of f in the presence of an impulse. In other words, if you really want to see how a system behaves, you just look at the impulse response. Now the impulse response is important, and in the last lecture we discussed any signal is simply a bunch of impulses with different magnitudes deferred. You can in fact remake the entire any signal as a summation of delayed impulses with different magnitudes. So if you know how the system will behave for one impulse, you know how the system behaves for all impulses, because again, an LTI system, right, for an impulse, if you know how the system behaves for one impulse, for a delayed impulse with a different magnitude, you know how the signal will look like. And then you can use the principle of superposition to sum up all the signals and get the original signal, and you can have the output. That's why impulse responses are extremely important, and the impulse function deserved a separate lecture. The last two, in fact, concepts of this particular lecture is one of sampling and the other of quantization. Now if you have a continuous signal, this is a continuous signal, and if you want to sample it, if we sample it at the same frequency as the original signal, the signal will look like a uniform waveform, because technically you're just capturing it once every cycle. You don't even know how the signal looks like. So let's increase the frequency to double. Let's double the sampling frequency. Now if you double the sampling frequency this time, at least you know, well, there is a crest and a trough. Here you only saw half the signal, half of the information, actually more than half. Actually almost all the information was lost, because you could not recover this signal from this step function, you couldn't recover it. The step function tells you as if the signal is 1 all the time. But if I double the frequency, I realize no, the signal has a crest and a trough in one cycle. But if we increase the sampling frequency to 10 samples per cycle, now you have a very good image of how the signal looks like. So, if you want to sample a signal, it's called the Nyquist theorem or the Shannon theorem, which says the minimum sampling frequency has to be double that of the original signal. Only then at least you can get some idea what the shape looks like. Of course, the more the merrier. The other concept is quantization. Now, if you want to quantize a signal, or if you want to make it digital in nature, you have to convert an analog signal, which has infinite number of possible options between 0 and the amplitude, into a limited number of jumps. So if you use a binary quantization, then as you can see, this is one level which is up and the other level which is down. So this is not a very good approximation. So let's increase the levels. Now in this quantization you have 4 levels. You can see 1, 2, 3, 4. Obviously this requires only 2 bits, 1 and 0. This requires 2 bits, 0, 0, 0, 1, 1, 0 and 1, 1. Again, this is a better approximation than this. You can also increase the quantization. So this is a huge level of jumps, and obviously this will require a lot more bits to store the information. But you can technically reach the same level as that of the analog, although it is not advised. So both sampling and quantization are needed. Sampling is done if you want to make the signal discrete, and quantizing is done if you want to make the signal digital. If you want to make it both digital and discrete, well, you need to do both sampling and quantizing. That was the end of this lecture. It was a very brief lecture. Next lecture we are going to talk about discrete Fourier transform, both 1 dimension and 2 dimensions. Thank you very much and have a good day. Assalamu alaikum.